So it could be a good use of our time to talk a little bit about the lab infrastructure a bit more. And I posted a couple of messages after Tuesday's class talking about simulation infrastructure and some possible ways to go about making your life a little bit easier for these last kind of steps of MP3. It's like anything else, right? An individual simulation and isolation is never that hard. The issue is it's never just one, right? You're simulating lots of small changes and confirming that the results are still what you expect. And that's the trade-off of I put a little bit more work up front. Getting to that first simulation is actually a little bit slower, but then the nth simulation is really fast compared to if each time you're kind of manually setting up things the way that you may like. And I posted a couple of examples in our Discord chat that you may find valuable, but you may not. Let me just mention that as well. So you may have your own thing going as a team. You may feel pretty good about how you're currently doing things. So in no way, shape, or form am I saying, do you have to do this? But I do think for MP3, this is kind of the biggest challenge that previous to this, the hardware driver interface was just via registers. And that's easy enough, I think, to simulate without needing all the software in the loop. And you can simulate the value of registers and confirm your design is fine. Input vertices and registers are basically it. Now you have code, and that is not trivial to do. So here's a couple of different approaches that I posted, both of them, but I'll just quickly walk through. I would just add that both approaches are successful. So you can do some hybrid, you can do just your own bespoke implementation. And I like both approaches because they're different ways of thinking about the problem. So this is from a team from last fall, and they put it together right around this point in the semester in the MP3 assignment. And I would just call this the cache simulation approach. And I know you're not Tickle experts, and I'm not either, but it's a declarative programming language. You should be able to figure it out or look for the right ways to do particular things that you'd want to do. It is meant for more advanced simulation and verification tasks than what we even ourselves are using it for. Generally, the question of, can I do X with this language is yes for Tickle. You just got to find the right syntactical incantations to get it to work. So this should look like your existing simulation scripts by and large, reset the system or reset that part of the core you're simulating, set it back down, get your clock up and going. You could have done this earlier, but get your clock up and going at that point. In this case, also initializing that program counter signal. Yours may be called something different, but by default you would probably have something like this. Provide, using probably your existing infrastructure, whatever you want your input data to be that you're simulating. I think for MP3, simulating just a single vertex in isolation is probably sufficient to then go do a board test. Say, okay, this was one vertex, but you can do multiple as well. What this approach does is it creates variables in the script itself that take in just the binary output of the assembler that we provide for you and just store that as a big variable array in the Tickle language itself, in the runtime itself, not in Vivado necessarily itself. That hex file is not something that I provide for you, but if you look at the driver and how we do the assembling, that's just an intermediate result. That's what gets copied to your DRAM in the device memory anyway. In the driver, you can just quickly write those two files, and that's there. That's going to be one or two more lines to add to your driver if you want to have this functionality. I don't think there's any harm in doing that. It doesn't do it for you, but otherwise it's basically the same. Splits it line by line. And then it takes those splits of those values, it actually does flush the cache, and then it takes those cache values, it's here. It doesn't actually necessarily need to convert it this way, but converts it to a binary value and then splits it into a string where it recognizes for the particular cache we have for a given address. Certain number of those bits are going to be the tag address. Certain number of those bits are going to be the line address. I also think for our 19 bits of tag, you can confirm this, and if I'm wrong, I'm wrong, but I also think that the tag bits are probably the same for every address in instruction and data memory that we're looking at. But still, this would be the accurate way of doing it. For the addresses we're generating with our starter program counter value, certain number of those bits are the tag. The remainder of those are the individual index is what we would call it in 381, that it goes into the cache. The row in our cache we're actually interested in there. And then the actual simulation is just setting those values and kicking it off. Flush the cache and run. That's Tickle in this example doing the majority of the heavy lifting and initializing those just array signals in the Verilog implementation of the cache to be the tag, the data, and the address fields needed to actually simulate your cache. That kind of works. I don't know. I kind of like that approach. All simulation is a hack in some sense, that this is setting signals directly in simulation that otherwise would be set indirectly through interfacing with other components in the system. So, a perfect simulation doesn't guarantee things will work on the board. It never does anyway, but in this case, it doesn't necessarily guarantee it. But if your assumptions about how the cache operates are correct, then the simulation that kind of manually sets those values should lead to a result that is pretty good. And here, a couple hard-coded magic value of how long it takes to flush the cache probably helps, so that once your simulation starts, you know that here's my actual signals that are happening here. So that's one such approach, and I think it's pretty good approach. The other approach I also posted is actually kind of replicating, and I don't know if anyone knows Ryan, but is attempting to kind of replicate some of the assembler infrastructure and kind of wrap it all into one package. I think it was easier for that team to kind of not try to grow out just a small part of it, but to kind of make sure they understood everything that was happening from GLSL all the way down to assembly to the actual binary result here. So a big part of this code is basically redoing in Python the assembly infrastructure. I may have mentioned that we used Lua. The person who helped me develop it really liked Lua. We could have done this way as well. So there's a lot of code in here that's basically looking at the assembly output and determining what the binary is going to be corresponding to that. And it's written in that Pythonic style that some people love and some people still need to get used to. So it takes as input now the assembly output from the compiler infrastructure, which is usually something that gets printed out if you have certain debug modes turned on. You save that to a file, you then run this file on it, and it's going to do otherwise a lot of the same things. The main, I can show where, so this is the assembly output that you just grab straight from the driver. It's going to then be specific to each shader application you're working on. But what it then winds up doing is, let's see if I can find the actual, where the simulation of the instructions is happening here. It's not actually working with the cache at all at this point. So what it winds up doing is every time there's a time to fetch an instruction, it sets the equivalent signals from the cache as being high and then low as needed to by the spec of the cache, but it's actually not fetching from the cache. So it doesn't actually initialize those data values stored in the cache. It just stores those directly and is actually grabbing those values from variables that are already defined. That is abstracting away basically the entirety of the cache. It does require you to, again, have a pretty good understanding of how the cache is already working for you to be able to do that, but then you have probably a faster simulation and one that you can really extend in various ways that the other one is pretty limited to interfacing with that cache. Neither of these, as I provided them, are kind of ready to go that you can just take and just make them yours. You have to kind of look at them, understand them, and adjust them for your purposes. They both make certain assumptions about how signals are named that may not be how your signals are named. So I feel comfortable giving these to you, knowing that you can't just say I'm done with my project now because I have this here. And I think in the time you have available, if you don't already have some infrastructure like this in place, it's probably a good idea to carve out one member of your team and say, get shader test or equivalent project kind of working for us so that we have more confidence that what we're simulating is correct. Any questions about either of these two examples? And they're both on Discord. You can take a look at them yourself. Okay. So where we left off, we got not distracted, but we were looking at inverse square root very briefly, and I just provided those links as well. There's not a quick explanation for how that inverse square root implementation works. It assumes that in a floating point representation, The integer field is actually happens to be a pretty good approximation of the log of a value, and then you can take that to calculate the inverse square root using Newton's method. So that was cool, but also a little bit besides the point. The point we left off on was just in working with the shader language, generally for the type of operations one expects, and they've kind of co-evolved together, the type of operations one expects in your graphics program are kind of just natively supported in the shader language corresponding to your graphics program. So that's a nice thing. That's a positive thing. Just things like your matrices and vectors being kind of primary types in the language. That's one thing that's a critical thing. Also just all the trigonometric and other kind of functions one tends to need to use when doing graphics programming. You tend to not have to write for a particular effect a large number of lines of code for your shader code. That does not necessarily guarantee, and that becomes a driver and architecture implementation detail, that does not necessarily guarantee that when you write power exponent or exponent 2 to the x power function in your GLSL code, it doesn't guarantee that there's a native instruction and a piece of hardware dedicated to accelerating that operation in either your driver or in your architectural support. But these things have all kind of been co-evolving with each other. And I think it's fair to say it's likely that there's a reasonably efficient implementation of that underneath the hood. So in general, you should use those functions. If you find yourself writing a lot of shader code, a lot of lines of code to get a particular effect, you're probably missing something that's already there that does it, I'd say, quite a bit simpler. So it's not just the calculator functions, it's also things that would otherwise require perhaps more branching in your code or just more lines of code, things like absolute value. Grab the sign of a particular input value, so that would return -1 for negative numbers, 0 for 0, and 1 for positive numbers. Minimum functions, maximum functions, clamping functions are a very common thing that we have to do where when we apply the math to a particular object or an attribute of our vertex, we do need to make sure the end result actually still falls within one particular range. That's a very common thing, and there's many others as well. Clamp is a very common one we see time and time again. So take a minute. And I won't make you partner up. There's only 5 of us here today. For this first example, and you can do both examples, given the functions that we have, and I can kind of bring it back to this slide as well, how would we write that first snippet, which is doing a decent amount of work? So given a minimum value, given a maximum value, given a value x, how would we do calculate a value f equals the minimum of a current maximum compared to an existing maximum value? Like any function call, you kind of work inside out. We first take the maximum of the value compared to a minimum value, and the minimum compared to a maximum value. That would just be clamp, right? That would be clamping x of minimum and maximum. How about this one? May or may not be a thing you would otherwise. This is a slightly more contrived example, but still, assuming x is not equal to 0 as an input to this, we want to calculate a value f. If x is positive, it should be 2.0. If x is negative, it should be negative 2.0. What would we use for this one?
2 times the, whichever one is the positive.
Sine, yep, 2 times sine of x. Sine, signum, whatever you want to call it, sine, 2 times sine of x, the actual positive or negative sine of x would give us that result. And we can play around with these functions in practice, right? We have the last example we were playing around with was the vertex shifter, because that's kind of the easiest one for us to play around with. I don't think inverse square root will necessarily get us anywhere, but if we wanted to make sure our x position is clamped to a certain range, right? We're scaling it, we're adding, we want to make sure that no matter what, it's between the range -2 and 2. We could do that, right? We could clamp position .x, -0.2 to 0.2. The end result isn't all that wonderful because it's getting clamped, but then what you wind up having are 3 vertices that form a line, right? Because you would have 3 values and it winds up disappearing for that reason. Let's clamp it in such a way that it's not so bad here. So how about we clamp the scaling instead? So float x scale 2 equals, let's use it that way. Let's clamp our x scale so that no matter what, That one never goes between 0.2 and 0.8. I don't know what our actual, well, let's make it like 1.2 or something. And then instead of scaling it times scale, we scale it times that x scale 2 there. So clamping in position was valid, but then you wind up where you have a triangle where all three x values are in a line, so it doesn't show up as a triangle. So now I think we do see that we're in the original version of it. It's looking kind of glitchy on my screen. Again, this is over a remote desktop, then connected to a projector while I'm recording the screen. Although it is interesting, you can see kind of almost what look like caching effects as it goes here. You can see that now our y is scaling via the original mechanism we used for scaling, but x is kind of limited in terms of how much it's scaling. So in this case, at least on the x-axis, it's never actually disappearing here. So clamp works the way it does, as one would intend. And I guess, all of these functions work the way one would expect them to. So your exponents, your powers, your logs, your sine functions, and things of that nature. There's all sorts of functions that will become a little bit more obviously relevant when we start to talk about lighting calculations. We so often need to know a couple of things about lighting sources in a scene. We need to know potentially how far away it is from a vertex or from a fragment. How far away are we? We oftentimes also need to know the angle of reflection of that light source to the normal of the either vertex, plane, or the actual fragment. We have to calculate how much color should basically be corresponding to that particular light source at that location. That tends to be calculated via calculating distance functions. So that does exactly what one would hope. Given a point in either a 3 or 4 dimensional space, you can do it in 2 dimensions as well, calculate the distance between those points. So x2 minus x1 squared plus y2 minus y1 squared, and the square root of all that. You could do that without having a distance function. I think the assumption is that's a common enough operation you would have support natively for that. Likewise, we're quite often doing a cross product as well. So given a light vector and the normal for a plane or for a vertex or for a fragment, calculate the cross product of those two. You then sometimes need to normalize the end result because we want everything to be unit vectors to kind of have the same intensity. So you have a normalized function as well. You also have vector relational operators, which sometimes it's harder to think of obvious reasons you would have those. So here we have, again, by default everything is a float, but you can design and can have variables that have Boolean values. So bool, as expected, bvec is a vector of Boolean values to give you the operation like equal. So given a value of p and q in these two examples, where those are the x, y, z components of p and q here, you can have an equal operator, which is basically a SIMD or vectorized equal operator. So because it's not equal, equal, then not equal, equal would give you false, true, false, and the less than and greater than kind of do what you would expect them to. Also not always common, unless you're doing some more functional kind of programming, you've any and all operators as well. So if any of that binary vector, Boolean vector is true, then the result is true, or only if all, so like an OR gate or an AND gate kind of operation for the Boolean vectors that you have here. So it kind of does what you would expect. Rewriting the length of p minus q, that's not worth the work. That's distance function you can kind of do. How about this one? Can we rewrite this function in one line of our GLSL calls? So we have an input. Think of it as a function. That's fine. P and Q. There is. I went by it pretty quickly. So we have it for equal, less than, or greater than. So you're right. So P less than Q. And what would we have to do with that result of P less than Q? Yep. So if any of less than P comma Q would kind of give you that exact operation sort of in one or basically two calls to those built-in functions. That one's kind of a hackneyed example, but if you imagine you're doing a lot of like sorting of geometry in some dimension, that would be a pretty efficient way to do it here. This is what a more maybe typical vertex shader would tend to look like. Again, we're going a little bit out of order here, and I still think that was the right decision, but there's things here that syntactically we can understand, but algorithmically don't necessarily make a lot of sense. but this is a pretty common looking vertex shader. And in fact, you could almost think of it as kind of a default shader. This method of having a built-in GL model view projection matrix is not the version that we are using, but this transformation, this operation is an extremely common step that we will see over and over again. We have to figure out how we're positioning objects in the scene, how we're viewing the scene. That's all about setting up this virtual camera model of our scene. The end result is a matrix, and we have to get that matrix into our shader code, and at the very least, the end result of a vertex shader is a calculated GL position. Given an input position, provide at least an identity transform of it, calculate an output position here. So that line or some version of that line, depending on what version of GLSL and OpenGL you're looking at, is going to be resident in all of your vertex shaders that have anything to do with real kind of 3D geometry here. Also very common is doing some sort of setup of a lighting model in the scene. I was kind of hinting at that a little bit, but you have a normal defined for each vertex. You're either going to do that lighting calculation in the vertex shader, in which case you would do the actual diffuse color calculation here, or you would push that to the fragment shader, in which case the vertex shader is just going to perform a pass-through of those attributes. But then you would see very similar looking math in your fragment shader if that were the case here. Given a particular uniform light position, figure out what the distance is between our light, calculate the cross product effectively there, and determine what your color needs to be based on what that light normal tells you is the relationship between your primitive and your light source. That one's not terribly interesting. Fragment shaders, it depends on what you want to do, of course, with all of this. We're still making do until MP4 with just pass-through fragment shaders, where we specified at vertex time that we want this to be an RGB value for our color, and it just passes that through and says, okay, at the very least, we should have some generated color for what our fragment should be, but there's all sorts of things, of course, you can do in your fragment shader if you want to change the color. You can do equivalent amount of math that we have here to calculate based on a light source what the color should be, or you can just mess around with the color at the time of your fragment shader. There is a fundamental difference between doing per vertex color calculations versus per fragment color calculations, beyond just the fact that, you know, the fragment shader runs a lot more than your vertex shader. That's a performance consideration. But from like the fidelity of the resulting graphics consideration, if you're doing things on a per vertex level, you're going to still see all the triangles in your model, if that makes sense, right? Because the same operation is happening for all your vertices in your triangle, and the only differences between your fragments is going to be dictated by your rasterizer, based on any gradients you have there. So you're going to have a lot of flat-looking triangles in your end result. That may be fine. If you have enough triangles, you can do a lot with a really flat-looking triangle, so that's fine. If you want something to look really maybe more differentiated on a fragment-by-fragment basis, then these kind of calculations have to happen then at the fragment shader. Conceptually, they're very similar. The difference is just kind of the expense of when you're running that calculation, once per vertex or once per fragment. There's lots of fun things we can do with color. Converting to grayscale, right? The same kind of math that you've probably done in software applications in the past becomes effectively one line of GLSL call. So taking your NTSC conversion weights to go from RGB to gray, we think of that as being kind of a matrix operation, and it sort of is, but you're just taking that weighted average. So the dot product works for that. Give me the RGB value and convert that to gray based on a particular set of weights. Once you have that value of gray, then you just set the RGB to the gray. You can do that for sepia tone and things like that as well. We can do all sorts of manipulation, as we saw, with combination of swizzle operators, arithmetic operators, and built-in functions for our GLSL code. This kind of stuff should sort of work for you. This is in the fragment shader, but you could also then do this in the vertex shader as well. So when it comes time to demo MP3, demo the existing applications. That's always important. You know, you should be able to show like what you did for testing and what you've been able to show beyond just the existing applications as well, within reason. The design flow should be basically, let's start with something simple in our shader. Let's confirm that the assembly output, which you can just look at the driver output, confirm that the assembly output doesn't contain any instructions that we don't support. And if it does contain instructions that we don't support, confirm that it's not that big of a deal, mathematically or arithmetically, or is it going to completely break everything we want to do? And then just run it and see, test those instructions via that mechanism and show that you're getting the end result that you're expecting here. For our cube flyby example, there's a couple things going on that are still going to make it a little difficult for your example to look necessarily as good as you would want. First, I already mentioned this, so that's why I didn't want to go too much into it, but in terms of what you have to add to the driver and what you have to be able to implement is this idea of setting these uniforms. And I would be a little careful assuming you have that all done if you just happen to have the shapeshifter example working. Shapeshifter.cpp does use those functions. We talked about this before, but first one is GL get uniform location. Our implementation of that is basically a pass-through. Give me the identifier that OpenGL provides for that, but not just that one, but then also the updating of those values. GL uniform, in this case, 1F. This is an example of OpenGL not being object-oriented in any meaningful sense, right? So for every different type of data that you may want to pass as a uniform, there is a different function in OpenGL to support that, for better or for worse. OpenGL used to be entirely like that there was a single function called GL color, and then there was the little suffix at the end that would dictate exactly what kind of color, how many dimensions, what was the data type going to be. For the most part, that's now gone in OpenGL, but it's still here in modern OpenGL for the uniforms as well. That kind of stinks from like a driver engineer workload perspective. So my suggestion to you is you support only what you need to support to get your applications running, because they're all doable, but each of them is an additional function that you have to write and test and confirm, and it's not a requirement that you get them all working. GL uniform 1F is relatively straightforward, in my opinion. It's a float. You have to check when you call this function that there's a location in memory, in data memory on the device that is effectively allocated for that purpose. We don't really write a memory allocator. We just kind of traverse sequentially through memory, 4 bytes, then 4 bytes, then 4 bytes, then 4 bytes for these data types here. You then set that value in memory. You then need to make sure, as we talked about before class started, after end of each frame, at the end of each frame, or when you get a new GL uniform call, I think end of each frame is probably the safer bet. You flush those caches. You invalidate those caches when that happens, because this is a location in memory you're setting. There's a cache consistency issue with regards to that your software application running in the shader core is going to be seeing the stale values of those uniforms if you don't flush the cache in between each frame here. I think it's okay to assume that each frame will have its own set of GL uniform calls, so flushing the cache each frame seems reasonable to me. But for uniform 1F, that's what it's doing. It's a single scalar value. It gets allocated a location in device memory. When you then get this call, and that's all bookkeeping logic, right, in the driver. Then when you get this call, it's a single SGP write 32 value of the given address for the uniform of the given value with conversion to our internal 16.16 fixed point representation. That's all that's happening here. For every type of data that we have, there is a version of GL uniform associated with it. And they're named, I would say, fairly consistently, but not necessarily super intuitively what they do. The other one we have that we are using in the cube flyby is GL uniform matrix 4FV. We can kind of look at it and figure out what it's doing. So GL uniform, set a uniform value. Matrix, we're setting a matrix. And I believe it's matrix 4, so we're setting I gotta confirm, is it matrix for a 4 length matrix, or we're setting it as a vector of 4 values? Matrix of 4 floating point values, and we're setting them as vectors at a time is what we're sending here. So we have to be a little bit careful when we have arrays in our C code and how that correspond to matrices in our shader code and the compiler, or excuse me, the driver that's then responsible for doing that interpretation of one to the other, because they're not the same. A matrix can be defined as a two-dimensional array, but it doesn't have to be, right? That's an implementation-specific detail. And there's different versions of this call that implement your matrix via different data types here. I think you're probably on safest footing just given the timeline we have associated with GL uniform matrix, with this application that we're expected to support that has this single call to GL uniform matrix for FV that we're providing as input. So the pointer or the handle to it, we're specifying that there's a single value we're copying with this operation. So the entire matrix, we're copying it. It does not have to be transposed. There's a little bit of a double negative there with that interpretation, and we pass it effectively a raw pointer to our C object or C++ object here that is going to have the next 4x4x4 bytes that we're then copying over to memory. The issue with this is it's hard to debug. Start with an identity matrix, because even if you transpose it, it's still correct. Right? Start with an identity matrix instead of this this viewing matrix that we have here, and then just do a scaling matrix instead. So instead of 1, 1, 1, 1 on the diagonal, confirm that 2, 2, 2, 1 works in your diagonal. Or 1, 2, 1, 1 works in your diagonal. You should have y dimension scaled by 2 and x dimension not scaled at all. And if that works, you probably can then go back to this code and it should be working. The issue otherwise is that when you're doing these kind of viewing matrices where you're dealing with perspective view from a camera into a scene at a three-dimensional cube, that if you get it wrong, and it's really wrong via the order of the bytes that you're copying over, it's going to look pretty random and really hard to debug at that point. But that's all this application that it's doing that is different than the shapeshifter. It is taking a single value that's being passed as a uniform, and it's using it for its matrix vector multiplication here. I don't happen to have it open right now. Let's grab it. This is the one that it's running here. It's labeled a little bit more differently, but otherwise it's the same. It's taking the position, attribute 0. That is our requirement. That's no longer an OpenGL requirement. We have to have it at location 0 because that's where we physically fetch our vertex attributes. We put it at location 0. Likewise for location 1, it's still a pass-through for color. And now what it's doing is it's taking a uniform that is that mat4 type, and we're performing that matrix vector multiplication. Take the XYZ value, concatenate a 1 at the end of it for our W value, do our 4x4 matrix vector multiplication. If the matrix is wrong, if it's transposed, if it's hasn't been changed, it's not going to look. It's going to look like random triangles in your scene. The other thing you'll see with this example, for better or for worse, is because it is three-dimensional, and all it's meant to be is here's a cube. So a cube just composed of triangles, but we don't implement all the other things that allow us to have 3D as of yet. We don't ever implement all of them, but for now, we're just panning a camera. If you look back at the code, we already kind of walked through it before. Every time I'm pressing the arrow key here, I'm just changing where I'm placing the camera in the scene, and then the matrix calls are exactly the same. It's using that GLM library, which just makes our life a little bit easier. We don't have to think about the matrix math. The matrix math kind of gets done for us. But the software application is itself doing matrix multiplication here, and then we are passing that final matrix onto our shader to do the final matrix vector multiplication, which is the correct way to do it. You could see it either way. I mean, you see other approaches in which we don't pass a single matrix as our uniform. We pass multiple matrices as our uniform values, and then we first do a matrix multiplication, and then we do our matrix vector multiplication. Arithmetically, that's equally valid, but that matrix part is uniform. It's the same for all of our vertices in our particular scene. To me, it just makes more sense to do that in the application and pass the final result, because it has to get done once per frame versus calculating it over and over and over again, because every frame you're having, or every vertex would then have to do it. But we pass that on, we get our final matrix, and due to the magic of our 3D viewing transformations, as we'll be talking about starting a little bit today, but then I guess next week is when we'll be getting to it, the end result is something that's positioned or is viewed by us as being positioned in three-dimensional space. we're missing a couple of things here, which is why even when you get this 100% working, it's not going to look like this. I'd like to query you, the class. What is your hardware implementation, even when, assuming you get the shader perfectly right, and it's doable. It's not a huge stretch goal. Just get the easier ones working first and then get this one working. It's still not going to look, it'll look okay-ish. Why is it not going to look perfectly correct? Pixel accurate, whatever you want to call it. This is a 3D cube. So one of the answers has to do with perspective. Somewhere along, and we have not covered that yet, somewhere along the line we have to do perspective division, which allows for that kind of foreshortening effect, right? This, I have lost my mouse, take my word for it. That triangle on the right-hand side should look, and maybe I can make it look more extreme. Let's see if I can add a little bit. It wasn't a major perspective view, but still, that triangle on the right-hand side, yellowish one, should look smaller than the one that's closer to the camera. And it does, right? I mean, we're seeing perspective there, that it does look smaller. And that's what, perspective is, right? People further away in the classroom, given my vision, should look smaller than people closer to me. You don't always want to have a perspective view. Sometimes you want to have a orthographic view where everything is completely flat, where you have a really far focal point. That's fine too. But for viewing traditional 3D scenes, you want to have perspective view. That requires an extra step that we don't do directly in our hardware. If you want to play around with that, for the software implementation, this should do nothing. But for your implementation, this would emit an additional instruction. You can actually just divide the position by that perspective value that gets generated. If you have division working, then you're fine for doing that. If you don't, you'll still get a result that looks good, just kind of the perspective isn't quite right is the best way to phrase it. There's something more fundamental we're not doing in our hardware yet for this result to look good. Again, I don't have the hardware version up, so you can't really directly compare it. This is our first software example that does something that the previous ones haven't. What does it do differently, besides the matrix? Otherwise, it is just, we have random triangles, right? That example that just sends a lot of triangles.
If it's a cube, are there like triangles behind it?
There absolutely are. It's three-dimensional. So if you look at the source for it again, the geometry of this isn't any more difficult, and it's a little subtle because everything is kind of normalized to 1 and 0. It didn't have to be. But you have depth information. We have a 3D, we have a third dimension to this, right? And that's, to make a cube, you do kind of need a third dimension. You could fake one by doing some of those operations yourself in the application where you're already kind of applying a synthetic camera view and turning it into two-dimensional, but that's what the graphics hardware is supposed to be doing for it. We specify our third dimension of our geometry here. We apply this matrix vector multiplication. We still have that third dimension. We still have that Z information. So what piece of hardware are we missing right now? And why is it not going to necessarily look good? We don't have our depth. We don't have a depth buffer at all. Our render output doesn't do anything with that yet, and you don't have to until MP4. So for better or for worse, it's because of the colors I chose here, it's still going to look roughly three-dimensional, and our eyes are pretty good at finding patterns where they don't exist. But the order in which we render the triangles matters quite a bit for this application now. And as you start to rotate it, that's going to become a problem, because depending on which triangle gets specified first, and I am sure I copied this example from somewhere else, and I can't recall. Those triangles are going to get overwritten by the triangles that maybe sometimes should be overriding them, and other times shouldn't be overriding them. And whether that's the case or not is a function of how we happen to rotate our camera. But the triangles are still being specified and rasterized in the same order. It's the depth buffer's responsibility to make sure that no matter when I'm trying to get this one back up to the front here. It's not rotating very well. I think I might have to press a button while I hit rotate, or it's page up or page down or something like that to get to rotate properly. But those fragments that are closest to us should always be closest to us. But the way we're rasterizing now, it's going to look more like rand triangle. They're not random, where it's painter's sort, right? The ones in the back get overwritten by the ones as we specify afterwards, subsequently, and so we get whatever's closest to us at the end. It so happens to work out that for certain views, it still looks pretty three-dimensional, because there isn't actually, once we've applied that transformation, there isn't actually a ton of overlap between, what should be these two triangles and what should be the triangles below it and above it. So it's going to look, for this kind of view, pretty decent, but it's not going to be quite correct for basically those two reasons. We can definitely go back to that example, after the fact. The other kind of stretch example in MP3 is our flat shading example, and we haven't covered lighting models yet, so really this is kind of taking on faith that this thing kind of sort of will work for your purposes, but it has to do with a lot of specifying material and light properties. So we will get into that eventually, but we think of light as being kind of like a white thing, right? Some degree of white, and it can be certainly for a particular scene, but independently in these synthetic lighting models that we tend to use, we have a certain color of light. We then specify material properties of our geometry that will dictate how much it reflects or absorbs blue, red, green, and to what extent. So you wind up specifying a lot of properties on a per vertex basis. And then otherwise we're doing the same kind of operations that we talked about in the previous slide. The main one I would expect you to not be able to support for MP3 would be the power operation. It's doable. There's, you can do an approximation of it. You can do repeated multiplication. There's ways one could implement it. But for now, you can maybe just treat it and replace this with the multiplication for both the specular component and the diffuse component, and you'll get a not great looking result, but you'll get something that works at least for your lighting model. The real stress test for better or for worse on Flex Seal is the amount of geometry here, and I think it'll be an interesting test for you. You can't test it until you have at least the MVP transform working, because it is also three-dimensional, so you still need to get that working. But that's our Flex Seal. I think the lighting source changes over time, so it'll very slowly kind of start to change colors here. That is just a random object from Thingsverse, then converted into a format that our little model loader could handle here. That is a lot of geometry, because you can't see it, right? That's how you know it's a lot of geometry. It's just the magic of just more triangles is all that's going on here. I don't recall the exact count, but it's adorable, right? So obviously it's using a lot of geometry here. That's going to stress test. Well, it still doesn't have the depth buffer. So from this angle, it's going to be whatever the order of the mesh happened to be for this model, and who knows. You should still be able to make out a seal, basically, but it's going to really stress test your MP2 implementation. And what you will also, of course, find is that once you have MP3 working, everything's going to really start to slow down in your implementation, right? You've gone from vertex to rasterizer with very little handoff to now vertex, wait a reasonable number of cycles for every vertex before you can start rasterizing. And for big triangles, it doesn't make a difference. The rasterizer takes longer than the vertex shading anyway. For these really tiny triangles, it makes a tremendous difference. The rasterization is probably just a dozen cycles each triangle. Shading is more than that. It's going to be exceptionally slow on your system. But if you can get it working, that'll be awesome. Again, it won't look quite right without depth shading here. Kind of an extreme between those two examples. So the first two, I do expect you to get working. Third, feel free to play around and see what happens. Likely outcome, at least from prior semesters, is things just kind of lock up, which is fine. But come up with some version 2.5 applications of your own, because I think it'll pay dividends depending on what project you choose to go forward, certainly for MP4 as well, that you have more confidence in what you're doing in the shader beyond just what's required to do multiplication and addition and the in FIFO and out FIFO stuff that Shapeshifter is requiring. And I think it'll be worthwhile if you do that. Finally, I think it's fun. We should play around with some shader code. Here are two examples using slightly older vertex and fragment shader syntax that I just kind of liked, so I brought here. And we can try them out. This is the Utah teapot model, which used to be just like one line of glut code, and it's getting kind of messed up here a little bit. We can take a look at the syntax for what that's doing real quickly here. Not flatten fragment, because that's the fragment shader. So it's running flatten.vert and flatten.frag. Flatten.frag is doing nothing. It's our pass-through shader again. Varying is the older way of specifying an input attribute. So you have that going on. Uniform time, varying color. So time is kind of a nice uniform to have if you want your demo that things are changing over some period of time here. There's a lot of code that's actually not being used in this example here. Set the color to kind of a reddish tint. Do my 3D math. That's what you want to think of that line as. And for right now, this is arbitrary. So let's try something different. But for now, take the z value, or take the input x value, calculate sine of 5 times x plus time times 0.5, and set that to be your z value here. So why does this not look particularly three-dimensional? Well, if we were to get rid of that, now we're back to a nice three-dimensional teapot. Why does it not look especially three-dimensional to us? It is. You have to take my word for it. Because it's all the same color. That's absolutely the right answer. We haven't talked about lighting and color and things like that, but when we come back to that, I want you to think about that this is three-dimensional geometry. If it's all just red, it is, you can't really see it. You can't really tell. There's all sorts of ways we could play around and set a lighting model. I don't think any of those are going to look particularly good for this example here because we're not specifying any lighting source. You can specify based on the distance to the camera. So one thing we could play around with is we could say, I already calculated the distance of a vertex from an arbitrary XYZ location, and I could just try that. Color is already defined as our output, so we could specify vec4 of D. That seems like one too many. Okay. Give me the red component of how far away I'm from an arbitrary location. I haven't thought this entirely through. That location is in the X dimension here. It probably needs to be in Z for this to look, yeah, because it doesn't look especially good. In fact, it doesn't seem like it's changed any. Is there a color gradient here? If there is, it's really subtle. Let's try from a location that's at a, looking off from a distance. How far away am I from that point? Might have to normalize it or something. Let's see. And it's white. Okay, so the distance might be too far. This is my challenge in trying to randomly generate examples without thinking about it. It's entirely right. Let's keep the color to our flat red for now for this example. Take just a minute or two. What kind of things you want to try out? You can think of, if we can go back to the listing of functions. It's not as easy as it seems to kind of play around with shaders like this because you still have to have a model of what's happening in a particular set of variables and what is valid scope for it. So for example, I'm setting color to that. So it's normalized color values that we're allowed to specify here. But trying to set it to something else wasn't necessarily working. Likewise for X, Y, and Z, there's a limited set of values that are going to probably make sense for this particular scene that we have here. You can look at this example. The other example, that's our tune shader, which given a normal and a lighting direction is actually just doing a set of bands. So there's an intensity, that's our light interacting with our normal, and it gets a value between 0 and 1. And what this shader is doing is it's just a set of if statements that's kind of like a lookup table, but otherwise it's just a set of banding operations that it's performing here. If the light has a high dot product, meaning it's kind of shining directly on that particular fragment, corresponding to the plane of that triangle we have here, it should be fairly bright here, right? High red, medium green, medium blue, otherwise slightly less red, otherwise slightly less red, otherwise relatively dark grayish kind of color that we have here. That would allow us to see more three-dimension, because now we're doing things on a per fragment basis that give you kind of a banded kind of color effect that you have here. So we can look at this and we can make some assumptions that our light source is over here somewhere, in our three-dimensional scene. Dot product is going to be the highest. It's going to be lower and lower and lower depending on where the normals are of that geometry here. So at least you can tell it is actually a 3D model. So between those two examples, and I'll leave the source code kind of side by side here, I don't have it set up that I can do both, but separately we can mess with either the vertex shader. You tell me I never saved the vertex shader would explain why it didn't actually run. Or the fragment shader here. Take just a couple minutes. Chat with someone nearby. Wake them up if need be. And see what, this is just playing around. There's no like correct or incorrect result. I've been trying things and kind of flailing here. You guys try things and see what you can come up with. Let's just take just a couple minutes for either of these two examples.
What do you think?
Three of you. Kind of collapse together, please. A little bit closer. You can still keep safe social distance, but discuss with each other. And again, my thought process was, you can do whatever you want. Valid GLSL and most valid C rules will work for you, but, come up with something. Make something up. That's our current teapot. X, Y do not get changed. Color does not get changed. Z just gets changed kind of arbitrarily. And you can kind of see a sine wave in there, right? I mean, I feel like I can see a sine wave in there, and it's the Z dimension that's getting that sine wave. So, yes, funky teapots. We should be able to rotate the teapot. I don't have enough confidence in my ability to do it. You would rotate things by changing this value, but then you have to calculate like angle. You have to do sine and cosine. Right? What is it? Sine, cosine, negative cosine, sine, or whatever it is there to get your rotation matrix in X and Y. We can try it. I don't have confidence it's going to work, so try something else. But of course, play around. Whatever you want to try, I'm willing to type in here and see what happens. Just take another minute. This is meant to be just think creatively what you can come up with.
Did you see if the distance would work out to save the file?
Didn't look like it. Didn't look promising. And what you don't have when working with shaders is there are some utilities that are available now, but you don't generally have, without using those utilities, a lot of inspection into what's happening, live, right? Debugging capabilities. There are some tools, kind of like the ones we're using to kind of trap the OpenGL calls in the first place, but you have to use one of those tools. Otherwise, it's very difficult to say, hey, I calculated this value of D. I, in fact, cannot do, printf. Certain systems allow effectively that, but in general, that will not work. See what it says. Yeah, not super happy about printf in my code here. So it is actually a little difficult to say for certain. Oh, that's not saved again. We're back to a more firmly read. I have a hunch that the distance. Okay, let's think about distance. We also don't have inspection because this code that I'm running, has a single line that says draw teapot, so you don't even see the raw geometry. I could probably find it somewhere. My assumption was the raw geometry was centered at 0 and effectively already normalized. That's oftentimes how we specify models that we're loading into a scene. That was my assumption, and then consequently calculating the distance between V and some arbitrary point at negative 0.1. Maybe the issue is that's too close. Nope.
Seems like D is big.
D is too large, right? We can see that, right? D is too large because we're getting basically max red, right? If we run this with 1, I don't think it's going to change any. Yeah, well, at least visually it doesn't look obvious that it's changing. I mean, we can just hack it. But the issue is not the intensity of it. The issue is that it's not changing.
Instead of D, if you try doing the absolute value of the Z component, I guess that's assuming Z is between like 0 and -1.
Well, that's something we can check. And that should be the stuff. Well, we'll see. That's what I wanted us to do. Okay, we can overanalyze and still get the wrong result, or we can play around with it. Well, let's do that while turning off the funkification of it here. So v dot z equals yellow vertex. Oh, I set v already, so we don't have to change. We can comment out that entire line. Okay, so v dot z should be the initial depth value. Oh, cool. That tells us something about what our depth information is here and where the camera is located. Because again, this application, it's not even that easy to change the camera. So there's two things you have to kind of wrap your head around, right? This doesn't look like Z information when we're staring at it, but that's the Z as the geometry is specified, and then the geometry gets moved by that transformation matrix. We may be able to make it look a little bit better by instead saying V equals that. Let's say V equals, we gotta be a little bit careful here that we don't do it twice. Oh, let's be especially careful. V2 equals that transform thing, and then now I think if we do it, that should be things further away should look darker. Brutal. Well, this is the problem in the experiment. VGL model view projection matrix times V, that should be the new geometry, taking V2.Z, we can comment out that, not that it doesn't matter, we'll overwrite it. Interesting. So abs of V.Z, before we do the transformation, still gives us that nice 3D effect. But after we do the transformation, all the values are 1. We could do get a little bit of color inspection of our geometry that way. That kind of tells us a little bit. We did RGB as X, Y, Z. Did I? Or did I do it backwards? That works. We talked about that this should not change anything because that's our swizzle operator, which is just a bit of syntactic sugar to allow us to specify the different attributes. It should give us the same result here, and I believe it did. X is R, Y is G, and B is blue, and its absolute value. That's why it kind of looks mirrored on here. Otherwise, if we didn't do absolute value and instead did we could also do min, because it's just a single value we care about. Not a bad idea for color anyway, right? To kind of clamp the end result and see that it falls within the expected range for color. Makes sense to me. If you, again, it is still rotated, I believe, but if you imagine a Cartesian 3D plane here with the origin roughly in the center of that teapot. Then you can kind of see X growing, you can see Y growing, and Z would be potentially coming out. It depends on where the ways the camera is set up. So you're seeing Z growing in this dimension. I like it. You know, you guys remember right-hand rule. So Z is coming out positive towards us. So I think that's correct for us here. We'll get tripped up when we talk about coordinate systems, and the nice thing, if you get it backwards, it's not that hard to change, right? You either have it in the right dimension or the wrong dimension, and you kind of just flip your sign around and you're okay. All right, that's a pretty cool. I actually kind of like it. I'm open to other suggestions. One more idea, and then we can get out of here. While keeping that color, I agree. Let's keep that color. So that's a winner.
What happens if you do
Wavy color or wavy? Everything wavy.
Move that v dot z line to after you set the color.
And I wonder, so setting it to be based on v dot x is kind of arbitrary. But if we just do that sine, I don't know, what, 5.0, I guess that would be the speed of the sine, right? So that makes sense. So that's like the frequency of the sine wave. Time would still allow it to be a shift. So I don't know why I did v dot x. If we just do v dot z as sine of v dot z, it looks pretty cool. It looks basically the same as what the v dot x1 was doing for us. But the whole thing is kind of shifting around now. I like it. Okay, let's leave things. I promise that would be the last one. Let's leave things here for today with the trippy teapot and funky teapot, yes. And we'll see everyone next Tuesday for MP3 Demo Day. Push hard on it. I look forward to seeing your results. Thank you.